Hello, welcome to our semiconductor education program. I'm Vincent Chang. I'm going to teach you an IC power amplifier part 2 bias, which means the DC analysis. Here's the LM380 IC power amplifier designed by National Semiconductor. If you can remember, in its data sheet, it says the output is automatically self-centering to 1/2 the supply voltage. In other words, the DC output voltage is approximately equal to the half of the supply voltage, VCC ground, so it's the center between VCC and the ground. So why? So now I want you to pause and try to solve this question, the DC output voltage by yourself. Maybe you can spend 5 minutes, pause and think. So before you move on to the next slide, I really hope you can try hard and think how to solve. At least you try how to start, where to start. So where to start? You should start from where? When you try to solve the integrated circuit bias, where to start? You have to find the reference current, right? And then what? Then what? The reference current will go through the mirror. So I already give you a hint, mirror. So I just remember when I was young, and I usually try to solve a circuit, a problem. I spend a couple of days cannot solve this, and I spend even a couple of weeks try to solve the problem. So I challenge you, try to solve this, to start this by yourself. So here's the input stage. I don't know if you find a clue, but I already give you a clue, the reference current. You start with the reference current, So what's the path? What's the path? So this is the path, right? So I reference, then I3, and then what else? The input emitter follower. And where's the ground? The base resistance R4 connected to the DC ground. So the reference current equals what? The reference current, if you neglect the current flowing through the R3, so reference current equals I3. So here's the supply voltage VCC. So where caused the drop? The voltage drop. So you have the VEB 11, and then VEB 3, and then what? The VEB 1. So here's the path. See the path. And then where's the drop? Of course, the drop will fall on the two resistors. One on the top, the R1, the other one on the bottom, the R4. But what's the current flowing through the R4? It's the base current. So compared to the emitter current, which is the I reference, so then we can neglect the drop across the R4. So assuming the rest of the drop will drop, the fully drop on the R1. So VCC deduct the 0.7 volt, the VEB, and divided by R1. And then the current will go through what? The mirror. That's the second clue, the hint. So the mirror R5, Q5, and then Q6. So what's the path? So where's the path for the I4? So the goal is to make the connection between two current, I3 and I4. So how to solve that? So also similarly, you can find the DC path. So then the emitter follower, right? The another emitter follower, the Q2, and also the DC ground. So by the same token, we can neglect the voltage drop across the R5. So here's the path. So this is the path. So now the I4 equals what? the DC output voltage, VO, and deduct VEB, what? 4, and then another one, VEB 2, and if we neglect the voltage drop across R5, then the rest of the drop will drop on the feedback resistor R2, right? So 2 drop. So VO deduct minus 2 VEB divided by R2. Then the current mirror will force these two current be equal. So I3 equals I4. I3 equals I4. So you're closer than you think, right? So the relationship between these two resistors, R2 and R4, R2 and R1 is what? Is 2 times. So R1 equals 2 times R2. So what's the value of R2? 25 kilo ohm. So what's the value for R1? So 50, right? So here's the result. So here's the outcome. So VCC is much greater than VEB. So you can neglect the VEB, 0.35 volt. Then the VO is approximately half VCC. So again, the output is automatically set self-centering to 1/2 the supply voltage. Let's move on to the output stage. We solved the input stage, and then let's move on to the output stage, the class AB output stage. So I want you to go deeper, try to solve. I know it's a little bit challenging for you to solve this. So you can also pause again, try to pause and solve this by yourself. Try to solve the quiescent bias current ICQ by yourself. So let's start with the diode, the bias current of the diode. So the ID, reference current, equals the ID. Why? The PNP current mirror on the top, Q11 and Q12, right? So the reference current mirror and to the diode current, the ID. So ID based on the diode relationship equals ISD, which means the saturation current of the diode, and exponential VD divided by VT, the diode drop. So let's try to connect the diode with the class AB output stage. So look at the green circle. So on the left, you have the 2 voltage drop. So on the right, you have what? You have the VBE. You can neglect the voltage drop across the very small resistance, 0.5 ohm, the R7, R6, you can neglect. So then the VB8 plus VEB what? Careful. Sorry. So VB what? VB9 equals 2 VD. So then the VD, based on the equation below, then the VD equals VT natural log. VT natural log I reference divided by ISD, right? So what's the next? The next, you can express the VB based on the ICQ. So based on the transistor's IC-VB relationship, so the VB equals VT natural log ICQ divided by IS. The IS means what? It's different from the ISD. So IS is the saturation current of the BJT, the saturation current of the bipolar junction transistor. So the IBE, in the same way, the IEB9 VT natural log IE9 emitter current of the Q9 divided by IS. So then you can write down this. We've seen this before. So 2, the natural log A plus natural log B equals what? Natural log A times B. So ICQ times IE9 equals I reference square, 2. There's a 2, so reference square. So we got one equation. So then what else? So what's another relationship between the connect, the ICQ and the IE9? So it's the blue node. So look at the blue node. So you can neglect the current going through the feedback capacitance. And then, so ICQ equals what? IE9 plus IC10. And then try to connect between the IE9 with IB10. So IE9, IB10, right, is similar. Collector current is approximately equal to the emitter current. And then what? Then for the Q10, base current, collector current, 1 plus beta. The beta M means the beta of the NPN transistor. So IB10 equals IE9. So now the second relationship connect the ICQ and IE9. If you solve these two equations simultaneously, here's the outcome. It's a very beautiful outcome. So expressed and very simple, right? So although the process is a little bit difficult, but the result is quite simple. The quiescent bias current is, if beta is 100, is about 10 times, right? Square root of 1 plus beta. So 10 times reference current. 10 times reference current. Very beautiful result. So here's the takeaway. Here are two takeaways. So number one, input stage bias. So remember how to solve this? How to solve this? How to conduct the DC analysis? Try to make the connection between the two current through the current mirror. The first one is on the left. The left-hand side of the mirror, I3. The second one is the current on the right, the I4. So you can link these two currents together, then you get this result. VO is approximately equal to half VCC. The second takeaway, try to solve. You learn this, right? Try to solve this class AB upstage, the bias. You can start with this, connecting remember the green loop, right? The two dial, the 2 VD equals 2 VBE, VBE plus VEB. And you will get this. And also the output node, you will get this one, the next one. So starting with the blue node, you will get this one, and solve these two simultaneously. If beta is 100, then the quiescent current is 10 times of the reference current. So I really hope you can learn to solve this commercial audio power amplifier. So I hope you learned something today through this lecture. Thanks for watching.